Hello, y'all. Welcome to lesson 74 of my DP chemistry curriculum. Today we're doing reactivity 1.3.3. We're going to be talking about fossil fuels, including coal, crude oil, and natural gas, which have different advantages and disadvantages. We're going to evaluate the amount of carbon dioxide added to the atmosphere when they burn, and we're going to understand the link between carbon dioxide levels and the greenhouse effect. So it's kind of a bit of stuff that we're going to have to go through, but let's start with fossil fuels. Well, where do they come from? These come from decomposing or decomposition of prehistoric historic organisms. And usually they have three categories that we kind of think about them in. So we have one which is coal. Coal is usually in the solid state, I mean, pretty much always. And with coal, mainly it's just carbon, mainly carbon, like solid chunks of carbon, but we do have trace amounts. We do have trace amounts of hydrogen, oxygen, nitrogen, sulfur, and metals. But most part, when we talk about burning coal, we're talking about just combusting carbon on its own. Next, we have crude oil. Crude oil. This is usually in the liquid state, and these are mainly long, oops, long hydrocarbon chains. For most of our examples, we're going to be using C8H18, octane. So these also do have trace elements. So they have trace, in addition to the stuff already in there, they have trace sulfur, nitrogen, oxygen, and metals as well. Hydrogen isn't trace because it's in the hydrocarbon chain. Lastly, we have natural gas. When we talk about natural gas, mainly this is methane. Mainly, whoops, methane, which, if you don't remember, it's CH4. Now, in addition, we also have trace small hydrocarbons, such as like ethane, two carbons. We also have water. We also have carbon dioxide. But for the most part, when we're talking about these, we're talking about either pure carbon, long hydrocarbon chains, or methane. So this is what I'm going to be referring to throughout this. Now, we've been using fossil fuels for a long time. The reason is they have quite a few advantages, so I'm just going to do positive. A couple of the advantages are they're highly exothermic, meaning we get a lot of energy from them. They're easy to transport. Natural gas being the hardest to transport because it is a gas. They are abundant. They're found in almost every country in some way, shape, or form, and they're relatively inexpensive. With all of these advantages, it's like, why would we not use fossil fuels? Well, they come with some pretty hefty disadvantages. When we either mine, use, or transport them, it's usually harmful to local or global or both environment, especially when we spill them in the environment, like the oil spill, British Petroleum oil spill, as well as literally many, many, many other natural disasters based in fossil fuel. Uh, Furthermore, they are harmful to humans in many ways. They can be toxic. They can be, when we burn them, they can create toxic byproducts. So there's a lot of ways they can be harmful to humans. Uh, they contribute to climate change. Some might argue that they are the reason for major climate change and global warming. And then lastly, they're exhaustible. They will end. We cannot produce these. They will eventually all be gone. We will run out, so we cannot rely on them forever. So there's some pretty hefty negatives. I would say I'm extremely biased as a science teacher that we should not be using fossil fuels. All right. So I said they're harmful to the environment. What that means is they're harmful in terms of the greenhouse effect. Well, this is one of the ways I'm going to talk about it. So what is the greenhouse effect? Well, first off, we have to learn about where it comes from. When we combust fossil fuels, our products, whether complete combustion or incomplete, we get carbon oxides. What I'm talking about are CO2 or CO, carbon dioxide or carbon monoxide, which these are directly correlated to increased temperatures, to increase global temp. So why? And that is the greenhouse effect, which is more the absorption. I'm going to just draw this directly from here. The absorption and re-emission of IR, infrared light, radiating from the Earth. So when the Earth gets hit by solar radiation, so let's just draw our big blue marble here, throw some green in it, and there is my Earth. We'll have our giant ball of fire, which is our sun, not to scale. And the sunlight hits the Earth, gets absorbed, and the Earth radiates that heat back out in infrared radiation, which would normally just leave the Earth, and that is energy leaving the Earth that had already come in. And when that happens, the Earth cools from the heat that it is initially taking in. The sun adds heat, the Earth radiates it back out, and temperatures stabilize for the most part. However, we have greenhouse gases. Greenhouse gases, when the sunlight hits it, reflect or re-emit in random directions. Some of those directions are right back into Earth. So some light is directed back at Earth. And when that happens, the Earth slowly starts accumulating this heat and light. And this infrared radiation is just heat. It is energy that is being transported, and it interacts with molecules within our atmosphere and within the Earth. It gets reabsorbed by the Earth, and it adds to the global temperature because this energy can no longer escape into space like it used to. The more greenhouse gases we have, the more this heat stays trapped. And so the greenhouse gases we're talking about are CO2. We've noticed that as carbon dioxide production and as carbon dioxide in our atmosphere increased, the global temperature increased with it. So what we're going to mainly be talking about now for the rest of this is CO2 production. So for the first section of this, we're going to pretend we live in a perfect world where all of our fuels are combusted completely. So let's look at coal. Coal is carbon, solid, plus oxygen, gas, and in a perfect complete combustion reaction, we get CO2. It even has a 100% atom economy for CO2, and it has a delta H of minus 393.5 kilojoules mole inverse. So for every 1 mole of carbon, we get 395 kilojoules or 393 kilojoules of heat. And once again, carbon is the only product, or carbon dioxide is the only product. So burning coal is just a great way to just shove out a whole bunch of carbon dioxide. For every 1 mole of carbon, you get 1 mole of CO2. Now, crude oil is a little different. For our examples, I said I'm going to be using octane, C8H18, plus, and I'm going to be using decimal coefficients, 12.5 oxygen gas. Sorry, this is liquid. That's going to produce a total of 8 carbon dioxides plus 9 H2O. Going to throw in my state symbols back. Now we see that carbon dioxide is not the only product, which is nice because it means that we're not only adding carbon dioxide. So not all of this is becoming a greenhouse gas of carbon dioxide. Water is a greenhouse gas, but it's a little bit better. So this has negative 470 kilojoules mole inverse. We're going to come back to these enthalpy values in a moment, so I'm keeping them off to the side. Lastly, we have natural gas, and that's methane, CH4 plus O2, both gases, produce CO2 plus 2H2O. And we have a 2 in front of this. This is also a very exothermic reaction of a delta H equaling negative about 890 kilojoules mole inverse. So just looking at the production of CO2, when we're burning coal, carbon dioxide is our only product, but when we're burning our other two fossil fuels, we at least split our products between carbon dioxide and water, meaning that we're not as efficiently creating carbon dioxide, which is good. We don't want to create carbon dioxide. So we can take these and we can now do a little fun math with it, which is where we can calculate the mole CO2 per megajoule. So how many moles of CO2 do we make per megajoule that we get out of it? We're using megajoule to keep our values relatively low. So when we look at coal, we get 1 mole of CO2, and we know that because we only produce 1 mole of CO2. And if we divide that by our energy, negative 393, and I'm going to use absolute values, 0.5 kilojoules, multiply the whole thing by 1,000 to convert kilojoules to megajoules, I find that I make 2.54 moles of CO2 per megajoule produced. So to produce 1 megajoule of energy, I'm going to make 2.5 moles of carbon dioxide. That may seem like a lot or may seem like a little. We don't really have a baseline yet, so let's look at crude oil. Crude oil, we notice, produces 8 moles of CO2, so that will be our starting point. But for 8 moles of CO2, we get 5,470 kilojoules. We'll multiply by 1,000 once more to convert that to megajoules, and we will get about 1.58 moles of CO2 per megajoule produced. So we can see that crude oil actually produces a lot less carbon dioxide for the energy it makes. While it makes more carbon dioxide in general per molecule, when we compare it to the actual energy production, it is more efficient at producing less carbon dioxide. So we might see that crude oil is a little bit better than coal in terms of combustion. Lastly, we have natural gas, methane. I'm just going to start using CH4. That also produces 1 mole CO2, but this time we have 890 kilojoules per mole, which we're going to multiply by 1,000 to convert to megajoules, and we find that we get 1.12 mole CO2 per megajoule produced. So from this energy conversion per mole, we find that between the three of our fossil fuels, natural gas actually produces the least amount of carbon dioxide per energy unit that we're looking at per megajoule, which tells us that natural gas might be the best in terms of reducing our greenhouse gases. But we want to look at other metrics too. There are many other ways that we can look at this. Another metric we can observe our CO2 production is through volume CO2 produced per gram of fuel. So once again, we're just going to be doing per gram. So we're going to look at 1 mole. So for coal, 1 mole of carbon is equal to 12.01 grams. We know that in 12.01 grams, we only produce 1 mole CO2. And CO2, as a gas, we can just multiply by 22.7 decimeters cubed, mole inverse, to find that 1 mole of CO2 is going to be 22.7 decimeters. So for every 22.7 decimeters cubed, it costs us 12.01 grams of carbon, meaning that we get about 1.89 decimeters cubed of CO2 per gram. So that seems like quite a little bit, actually. That's only like 1.89 liters, so almost 2 liters of carbon dioxide per gram of carbon we burn. When you say it like that, it actually sounds like a lot more, and it kind of is. So let's now look at crude oil. Crude oil, we use 1 mole of octane, CHH18, which is approximately 181, oh, sorry, not 181, my apologies, approximately 114.26 grams. This instead produced 8 moles of CO2, which 8 times 22.7, that is 181.6 decimeters cubed. We're going to set that over each other, so 181.6 divided by 114.26, and we find that crude oil makes approximately 1.59 decimeters cubed gram inverse. So we make approximately 0.3 liters less than we do with coal. So it's a little bit more efficient, but we can kind of tell that because we know we're producing also less carbon dioxide per energy, even though these are different values. Lastly, we'll look at methane, CH4. For 1 mole of CH4, that's equivalent to 16.05 grams. We only produce 1 mole CO2, which we already know is 22.7 decimeters cubed. So 22.7 decimeters cubed divided by 16.05 grams is going to give us 1.41 decimeters cubed gram inverse. So once again, looking in terms of volume of CO2 produced, natural gas is the winner in producing the least amount of CO2 per mass of fuel. The last metric that I want to look at before we finish this talk on fossil fuels is the energy released. Energy released per unit mass. So this is the energy per mass of fuel burned. With this, we can just do another simple calculation. We know that coal produces 393.5 kilojoules. We know that it weighs 12.01 grams per mole. And what we're going to do to make these units a little nicer is we'll multiply 1,000 on the top to get to megajoules and 1,000 baht on the bottom to get to kilograms, which essentially means we're doing nothing here. And we find that we make approximately 29.3 megajoules per kilogram of coal burned. For crude oil, we said makes 5,470 kilojoules for 114.26 grams. And once again, we'll do the 1,000 thing here, so they'll cancel out. And we'll get approximately 42.3 megajoules per kilogram of crude oil burned. Lastly, we have natural gas. Natural gas made 890 kilojoules per 16.05 grams. And we do the 1000, 1000 thing, and we get about 50.0 megajoules per kilogram burned. So we finally see once more that we're producing more energy with natural gas per gram than anything else. And one of the questions you might have is why don't we use it as much? And that's because as a gas, it's harder to transport, it's harder to contain, it's harder to move than a solid like coal or a liquid like crude oil. With all this said, there's one final metric we want to look at because this is important. What about the tendency to undergo incomplete combustion? So we don't want incomplete combustion. When you undergo incomplete combustion, a couple things happen. One, you get less energy. For a second, you make harmful products like carbon monoxide. And lastly, it's just more of a hazard. It's hazardous because then that means you might have some fuel left over that hasn't combusted, and then you can have that sitting waiting as like a ticking time bomb. So we want things that have a low tendency to incomplete combust. If we look at coal, coal has a lot of impurities. And due to these impurities, it ends up having a high tendency. You can kind of see that too. Some people do that thing called rolling coal in their trucks and they put a whole bunch of smoke and soot. They're just bragging that they can incompletely combust their coal, which is what they're doing, and produce a lot of toxins and carbon monoxide and aerosolized carbon. So coal has so many impurities that it has a very high tendency to incomplete combust. It's very easy to make it combust poorly. Crude oil is definitely better. It has those long hydrocarbon chains, and those chains need more oxygen. If you notice in our reactions up here, all the way at the top, we just generally need a lot more oxygen than we do in coal or natural gas to combust the crude oil. And because we need so much more oxygen, quite often that leads to some tendency to incompletely combust. Lastly, we have natural gas. Natural gas is small. It takes a little bit of oxygen. Whoops. Little oxygen to combust. So natural gas tends to have the lowest tendency of incomplete combustion. So as we look through these, you should be able to properly analyze each of the three main types of fossil fuels, analyze their reactants, their products, their tendency to combust, their effect on the environment and global temperatures, as well as you should be able to calculate things like volume of carbon dioxide produced or energy released per unit mass of fuel, as well as look at their tendency to combust properly. So I hope this helps you have a little more complete picture of this and have a great day.